Most of the world's divergent plate boundaries are on the ocean floor, in the form of mid-ocean ridges that spread apart. Divergent plates are when two plates move apart in opposite directions away from each other. This happens above rising convection currents, and these rising currents push up on the bottom of the lithosphere, lifting it, and it flows laterally or to the sides beneath it. The lateral flow causes the plate material above it to be dragged along in the direction of the flow. At the crest of the uplift, the overlying plate is stretched thin, and it breaks and it pulls apart. When a divergent boundary happens beneath oceanic lithosphere, as in the top picture that you see, the rising convection current below lifts the lithosphere and it creates a mid-ocean ridge. The forces that stretch the lithosphere and produce a deep fissure, the fissure opens and pressure is reduced on the superheated mantle material that's below. It responds by melting, and the new magma flows into the fissure. A fissure is like a crack. The magma then gets solidified, and the process repeats itself. When a divergent boundary happens beneath a thick continental plate, like you see in the lower picture, it pulls apart, and it's not as vigorous to create a clean single break through the thick mantle or through the thick plate material. So the thick continental plate arches upwards from the convection current lifting on it, and it pulls thin by the forces pulling it apart, and it fractures into a rift-shaped structure. And as the two plates pull apart, normal faults develop on both sides of the rift, and the central blocks slide downwards. So earthquakes happen as a result of this fracturing and movement, and early in the rift-forming process, streams and rivers will flow into the sinking rift valley to form a long linear lake. As the rift flows deeper, it might drop below sea level, allowing ocean waters to flow in. This will produce a narrow, shallow sea within the rift, and the rift can then grow deeper and wider. The rifting continues, and a new ocean basin could be produced. A convergent boundary are where you see plates that are moving towards one another, causing collisions. When continental crust and oceanic crusts collide, the thinner and more dense oceanic plate is what sinks into the ocean, and the thicker, less dense continental plate then overrides it. The oceanic plate is forced down into the mantle in a process known as subduction, and as the plate descends further or goes further into the mantle, it is forced into a higher temperature environment. So at a depth of about 100 miles, the materials in the plate that is bending underneath begins to approach their melting temperatures, and a process of partial melting begins. Now we're looking at the top picture, and this partial melting produces magma chambers above the subducting ocean plate, and the magma chambers are less dense than the surrounding mantle materials and are buoyant, so they float. The buoyant magma chambers begin to slow, and they slow as they rise through the overlying materials, melting and fracturing their way upwards, and the size and depth of these magma chambers can be determined by mapping the earthquake activity around them. If a magma chamber rises to the surface without solidifying, the magma will break through in the form of a volcanic eruption. What landforms are formed at this area are subduction zones, trenches, and volcanic mountain ranges. Destruction of ocean crust occurs, and we have deep earthquakes in these regions. Looking at the picture, the second picture, which shows oceanic crust meeting oceanic crust, we see that as these two crusts come together and collide, they subduct beneath one another. So one of the plates will subduct under the other. Normally it's the older plate that will subduct because of its higher density. The subducting plate is heated as it is forced deeper into the mantle at a depth of about 100 miles, and magma chambers are produced as a result of the melting, and the magma is lower in density than the surrounding rock material, so it begins to rise by melting and fracturing its way through the overlying rock material. Magma chambers that reach the surface break through a form of volcanic eruption cone and break through to form a volcanic eruption cone. And in the early stages of this type of boundary, the cones will be deep beneath the ocean surface, but later they grow to be higher than sea level, so this produces an island chain. With continued development, the islands grow larger and a larger landmass gets created. In these areas, also we see deeper earthquakes, ocean trenches, and the lithospheric crust becomes destroyed. In the last picture, the lower picture, you see continental crust meeting continental crust, and in this area it's difficult to actually draw this, but it's when two thick continental plates collide, both of them have a density that's much lower than the mantle, which prevents them from bending or subducting. So the heavier of the two lithosphere might break free, but they actually kind of crumple the crust. So fragments of crust or continental margin sediments might cause deformed rock. So this compression causes what are called folded mountains, and faults and folds occur in this area. Crust is not destroyed, it is not created, it's just crumpled or folded, and shallow earthquakes occur here. A transform plate boundary is a location where two plates slide past one another. The fracture zone that forms a transform boundary is known as a transform fault. Most transform faults are found in the ocean basin and connect offsets in the mid-ocean ridges. A smaller number connect mid-ocean ridges and subduction zones. A smaller number of transform faults cut continental lithosphere. The most famous example of this is the San Andreas Fault Zone of western North America. The San Andreas connects a divergent boundary in the Gulf of California with the Cascadia subduction zone. Another example of a transform boundary on land is the Alpine Fault of New Zealand. Both San Andreas Fault and the Alpine Fault are shown in many plate tectonic maps. In these areas, you will see that there are shallow earthquakes and there is no volcanic activity. The reason that the earthquakes are usually shallow is because they happen between the plates and they're not involved in subduction. Volcanic activity is normally not present because the typical magma sources that rise in the convection currents or melt in a subducting plate are not present.